Okay, hello. Am I on? All right. Welcome back to Data 100. We're on lecture number 24. As a reminder, we only have 26 lectures in this class. And so this Thursday will be our last lecture. This is like the last week of class. And then next week, we're going to have our final on Thursday. And instead of having lectures during our normal lecture time, we will have final review sessions Monday and Tuesday of next week. And on Wednesday, we're going to take a break, but we'll hold office hours to help you study for the final. Okay, so this is it. We have a few lectures left. And for the last week of lecture, I want to keep things relatively light, so I won't be doing super complicated topics. But I will talk to you about, I'll just try to give you like the broader picture of data science. And one of the broader pictures of data science that I'm going to go over today is how data is used in industry, in organizations, to draw conclusions from the data that they capture. Okay, so I'm going to talk to you today about data analytics and Spark. Yeah, Danny?
Will you be taking attendance next week?
Yes, we'll be taking attendance next week for the final review sessions. But we'll give we'll give two freebies for Wednesday and Thursday. Yeah. Okie dokes. All right, so I have here, these are not my normal slide templates, and that's because one of the former instructors for this class, Joey Gonzalez, has put a lot of effort into making these slides like super high production value, so I hope you're entertained. Okay, so when people talk about data in an organization or data in an enterprise, there is a lot of buzzwords and lingo that people use, but most of the buzzwords have some meaning, and so it's good to know what those buzzwords are referring to. Okay, so in the ideal world for a data scientist, we have all the data on one place. So ideally, we can like log onto a company computer and like pandas.read CSV, a giant CSV file, and just work with all the data in the company. But in reality, usually every team at a company has their own database. Okay, so each of these little like silver towers there is like one database, and it's very often the case that every team, or even the same team in a company, will have multiple databases. And what you have to do as a data scientist is figure out how to get access to all those data. Okay. And so, in a company, operational data stores are the databases that teams use like as they're working. Okay, so an inventory team will be like updating the database as they move products in and out of a warehouse. And so these are like the live production databases that people are using. There's many of them, and they're mission critical, which means that if you break them or cause one of them to go down, that whole team may stop functioning because they can't record down what's going on in the organization. Okay. And so because they're all managed by different teams, they all have different schemas, which means that they have different table names, they have different table formats, different granularities, right? Different temporalities. And they're not that useful for data analysis because they often don't maintain the history of changes. So for data science work, we want access to a clean historical snapshot of the data. And so companies have what they call the data warehouse. Look at the animation. So in the data warehouse, what we do is we take the live databases that teams use across the company, and we will copy that data into a big database that isn't used like on the go by other teams. Okay, so what we're doing here is we will ETL the data from the teams onto the big data warehouse. And the reason why we do that is to keep it safe from ourselves. If we mess up the data warehouse, the teams will still function properly. Okay, and this ETL word means extract, transform, and load. And it's you'll commonly see that word being used as a verb. So you'll say something like, "Oh, I ETL'd the data from sales into our warehouse yesterday." Okay. So in the first step, what we do is we extract the data from the data that's used in the operational data stores. And what we'll do is we'll take a snapshot of that data. We'll make a copy of it at a single point in time. And what we'll do there is we just want to make sure that when we run our queries on that data, that we don't affect anything in the rest of the business. Okay, so this part is not too easy. This part is not too hard. It's mostly just making a copy. Transforming is more difficult because every team in a company just defines their own schema most of the time. So most of the time, teams will just decide amongst themselves, okay, this is what we want to capture, this is what we want to record, and of course all the column names are named differently, so if you want to do a join, you have to figure out what column names are referring to what. And so in the transform step of ETL, what we're trying to do is take the data across different teams and wrangle them into a format that we can use to analyze. Okay. And so how is this data organized once we get it into a big database? Sometimes, or what we'd like is to have a big table. So in this table we have here corn and food, and it was sold. We sold 25 corns on March 30th to Omaha, and we shipped it to Nebraska. Okay. And this is a big table. And this is like we could imagine making a big table like this, where one row captures something about every single table in the entire company. The problem here is that when you make tables like this, you often have a lot of redundancy. So for example, in the last column here, you'll notice that Omaha, Nebraska, USA appears like 7 times. One for every single product that was shipped to that location. Okay, so the idea here is if you make a huge table, you have a lot of redundancy. And so instead of making a huge table, you'll have several smaller tables. And what we'll do instead is make what we call a fact table. In a fact table, all the columns here are foreign keys for other tables. So for example, we might have a locations table, a products table, and a time table. And what we'll do here is when we want to create or regenerate that large table from before, instead of having to remember Omaha, Nebraska 7 times, we can just say that, oh, okay, all of these rows here went to location ID 1, and if I do the join across the locations table, I see that they're all going to Omaha, Nebraska. Okay, so this is what we call like the cube of data, and by cube of data we just mean that each of these tables is called a dimension table because it's describing one dimension of the fact table, and because of that we have essentially this like cube metaphor to describe like, okay, we have times and products and locations to describe every single row in this fact table. Okay. The reason why we do this is to minimize redundant information. So if I want to update, if I misspelled Omaha in this database and I want to update that spelling, I just have to update it here, and I don't have to update it in the 7 times it appears in this table here. Dimensions are easier to manage because they're not the entries in them are not duplicated. And this is what we call a normalized representation, where we avoid duplication. Okay, so whenever it's commonly the case that we'll store data in this way, and when we want to do some analysis, we'll do a join on the fly. Okay, so if we want to look at products and locations, we'll join the locations table with the fact table with the products table, but that's not too hard to do. And it's something that's commonly done all over the world every day. Okay, so this gives rise to what we call the star schema. Look at that animation. And if I put the fact table in the middle and put the dimension tables around the fact table and draw little lines connecting the foreign keys to the primary keys of the dimension tables, we'll see that it looks kind of like a star. So if I like draw little circles on top, we're going to get this picture. And you can imagine many other tables that kind of surround this fact table here, like that. And it's also commonly the case that stars will be linked to other stars. And so we get what we call a snowflake schema, where we have like one fact table in the middle, but then every like group here has its own fact table. And it's commonly the case that in companies you'll just have like hundreds and hundreds of tables. And if you want to do anything with data analysis, you have to join like 10 tables together. And the way you figure out what's going on is by figuring out which tables are your fact tables and which tables are your dimension tables, and figuring out the pathing to take to like look at the products, look at some description of Omaha down here, and link it to some characteristic about a user up here. Okay. Okay, so OLAP stands for Online Analytics Processing, and what OLAP refers to is in an organization, what often happens is people have data and they want to figure out some pattern in the data. In other words, they want to perform EDA on the data that's recorded in the company. Okay, so what happens inside of an organization is that we have data analysts and data scientists looking at the data, making plots usually, or making visualizations of the data, writing reports about it, and then giving those reports to managers or other people higher up in the organization that make decisions. Okay, so this often involves creating like SQL queries. So if you look at data analyst roles, many of them will involve writing SQL because most of the data a lot of data in industry is stored in a SQL database. There are also tools that construct queries using, for example, a block-based language. But the important thing to note here is that a lot of times this sort of procedure, the OLAP procedure, doesn't require you to write Python. Instead, you can write SQL and work with tools like Tableau to make visualizations. So this is what's commonly referred to as business intelligence. And people often in companies create dashboards, and you can imagine that each of these plots here inside of my screen is a SQL query that runs on the data warehouse, and then it gets transformed into a plot, and it's displayed. And once you create that thing, you can show it up to like your CEO and say, hey, we should probably like spend more money in advertising in Omaha. Okay. Any questions about this? All right, cool stuff. So we've gone over operational data stores, which I have on the left. These are the data stores for each team. I've gone over a data warehouse, which is the data scientist like domain. Okay, so we ETL the data from the operational data stores into the warehouse. We've gone over how to store that data in terms of star schemas, and OLAP, which refers to the practice of making visualizations or doing EDA on the data in the warehouse. There are other types of data, however, such as text or log data, and photos and video data. And these data are harder to ETL because they don't come in a tabular format. Right? So how do you make a row in a data frame that describes a photo? It's a little hard to do. And so what's happened within the last few decades or so is that companies are getting access to a lot of unstructured data, like just text data, like emails, or photo or video data, like YouTube. And they want to figure out how they can do analysis on this data, or even store it in the first place, because it's not obvious how to store this data in a tabular format. And so what happens here is sometimes what you can do is just store the photos and videos in your database as like files, and then draw out some schema every time you load the picture. So what you could do is, for example, like just take the image data and just put it in that table. But it's kind of hard to do analysis because all you have access to here are, it's hard to imagine. Like, what do you have access to? You have like access to the pixel values maybe. But in any case, it's kind of hard to imagine how you would store this data in a tabular format. And so enter the data lake. Okay, so instead of having a data warehouse, what's happened in recent years is what we call a data lake. And the difference between a data lake and a data warehouse is that in a data lake, we just dump all of our data inside of there without a schema, without a tabular format. The nice thing about a data lake is that we store all the data in one place. We store it in its original natural form. So what we'll do is we'll put all our video files in a big folder in a data lake. And what this allows us to do is it allows the people doing analysis on the data to decide for themselves how they want to analyze it. So if I want to look at videos, I can query myself the lengths of the videos. I can query some like frames in the video to see if there's a cat in the frame. And this is what we call a schema on read method, where we store the data in an unstructured way, like not in a tabular way. And when we read in the data, we'll put a schema on top of it as we read it. So yeah, Danny?
What does natural form look like when it's not in tabular format?
Yeah, so when it comes to, so the question is, what does natural form mean when we're talking about this sort of data? If you have images, they might come to you in like PNG format or JPEG format or GIF format. And to store data in its natural form essentially means to keep the images in the GIF format and not putting it in a CSV, more or less. So if you want to put an image into a CSV, what you could do is like define some numeric features from that image. So you can say like, okay, I can store the brightness of the image in one column. I can store like how many pixels there are in the image in another column. But that requires some transformation. And if you don't keep around the original image, then you won't be able to get back the original like image, like what the image looks like. And so to keep the data in its natural form, what we're referring to here is we're saying if we have photos, keep them as photo files. If we have videos, keep them as video files, and don't put them in a SQL database. Okay. And so it's nice, but there are some problems with this approach. What we have now is the dark side of the data lake. Look at that. And so industry has gone through this shift in the last few decades where before everyone was very concerned about having a good schema, having very structured data. And these days people are of the mindset of, well, we don't really know what we want to keep track of, so let's just save everything that we possibly can and just put it in a data lake. But the problem here is that when you save everything, sometimes you save stuff that isn't really useful to you for analysis. And so what happens is you get some data that isn't that useful to you. And you also have limited data governance and planning. So for example, if you have this file, people just kind of throw files in the data lake and they name them all sorts of things, and it's pretty hard to interpret like what this data file is used for if you name it Joseph Big File 3.csv with JSON. Okay, and because you're not doing any transformations on it, your data here are usually just super messy, and what that means is that you have it's pretty hard to use this data. Because you're not storing data in a relational format or a tabular format, you can't use SQL, and you can't use a lot of other tools that assume a relational format or a tabular format. Okay, but there's a bright side. The bright side is that we now have some know-how. We have some data science know-how. So we can go back to the bright side. And so for data scientists bring a lot of new skills to the table. We know how to do distributed data processing, how to do data cleaning for large data sets. We have techniques like machine learning and computer vision and statistical sampling to deal with the fact that to diagnose problems in the data and to work around them instead of having to just give up when we encounter missing data. The technologies themselves are improving, so SQL databases are getting more advanced and can handle larger files. And it can handle, so SQL databases nowadays can also handle like more types of unstructured data. And sometimes they don't require everything to be in a tabular format too. Organizations are evolving, so organizations are getting better at like identifying where problems can arise in the future with data. And so hopefully, if you join a company, they'll name their files well. They'll have like tables that are named properly, and you won't have to like trudge through a bunch of mud to figure out how to do some data analysis. Okay, so the position in companies that are labeled data engineers are typically roughly like revolved around this idea of processing data from all over the organization and storing it so that other people in the company can make use of that data for analysis. Okay, so it's a very rough description because a lot of the data science roles in industry are being like actively defined and changing all the time. If you go to 10 different companies and ask them what their data engineers do, you'll probably get 10 different answers. But in general, this is a pattern that we notice, which is that data engineering positions in companies typically involve the ETL, storage, and preparation of data for other people in the company. Okay. So if we have tons and tons of data, we need tools that can handle large files across multiple computers. In the real world, we don't really have access to supercomputers, and instead what we'll do is have a bunch of regular old computers, but those regular computers fail often. And so what we want to do is do data processing on huge data sets of like terabytes and petabytes quickly and easily. typically this means that we need to use what we call distributed file systems or distributed computing. In distributed file systems, what we do is we spread the data across multiple machines because oftentimes it's the case that you have too much data for one machine to hold. Okay? In distributed computing, what we're doing here is we're running a program, but that program runs across multiple machines. So in yesterday's lecture on Ray is a tool that we can use to perform distributed computing because it allows us to run Python code, but then it will take that Python code that we run and distribute that Python code across multiple machines to run Python code in parallel, which gives us some speedups. Okay. Talking about distributed file systems. So if we have a big file, one problem that we have is being able to access it all the time. If it's too big for any one computer, what we'll try to do is store pieces of it across multiple computers. So we'll take that big file, we'll split it up into 4 parts, for example. And what we'll do is we'll take some of the parts and give them to some machines, like so. Okay, so I'll take B, put it across these 3 machines, take C, take D, like that. And so we can see here that each of the machines doesn't have to record down the entire file. And the benefit here is that if we want to, look at that. If we want to read in the file, we can read it in parallel. So if I want to ask for the entire big file in one go, I can have machine 1 give me part A, while I can have machine 2 give me part A, while machine 1 gives me B, so on and so forth. So I can read that file very quickly. These are often built using what we call cheap commodity storage devices. In other words, it's stuff you can get by going on Amazon or going to like Best Buy. Okay, so usually in industry, people don't buy like super specialized hardware. These days what we try to do is use cheap hardware, but have algorithms that deal with the fact that cheap hardware often fails. Okay, and what we mean by failure is, let's say that machine, here we go, let's see, machine 1 disappears, it blows up. Machine 3 lights on fire and melts down. But you can still read in the whole file by getting A, B, C, and D from machines 2 and 4. And then what you do when you have that file is that you can now recreate machines 1 and 3. You can replace your computers and still be able to like read in your data. Okay. Distributed computing. I'm going to talk a little bit about Spark, which is kind of like today's like industry standard for working with large-scale data processing. It was developed here at UC Berkeley by professors in the AMP lab. The AMP lab has now transformed into, I believe, what's called the RISE lab. So if you hear RISE lab or AMP lab, I believe those refer to the same like kind of group of people working on the same research projects. So again, this is one of the research projects here at Berkeley that we built and it kind of took over the whole world, and now it's kind of the standard for distributed data processing. Okay, the key idea in Spark is we have what we call resilient distributed data sets. And the key abstraction here is that in a Pandas data frame, if you read in that data frame in Pandas, if your computer crashes, you're gone. Like your data analysis is toast. You have to rerun your file. But if your file gets wiped out, let's say your notebook gets wiped out too, now you're super toast because now you don't have access to like your data analysis or your file. And the idea here is that Spark will take your data set, distribute it across multiple machines, and it'll hide from you the fact that if a machine goes down, it'll hide from you the fact that a machine might go down by automatically behind the scenes doing that distributed file storage thing that I showed in the previous few slides. Okay. And so in Spark, oftentimes what we'll do is we'll have a data frame, a really big data frame, and we'll do some transformations on it, like data cleaning or data processing. And we'll perform these operations in what we call a lazy manner, where we'll ask Spark to do a bunch of mapping or filtering or group by operations on the data. But these transformations by themselves don't actually perform any computation. What happens is when we ask for a special set of actions from Spark, only then does Spark go and actually trigger the computation that we want to do. In other words, we can tell Spark a recipe for doing a data transformation, but it won't actually cook the data until we ask it for its result. Okay, so I had here an example, but I'm going to skip the example to show you some code. So exit out of here. Hello. All right. Let's go. Hold on. Whoa, my video stopped. Okay, hold on.